This is Math 1151. We are ready to start. Last time we covered the chain rule. This time I'm going to answer this question here, and we'll see what's going on. So the problem is, find all points. Find all points on the graph of f of x equals x cubed minus 6x, where the slope of the tangent line is minus 3. Find all points on the graph of that function where the slope of the tangent line is minus 3. What tells you the slope of the tangent line? I hear the crowd murmuring to me the derivative, and so we're going to take the derivative. So solution f prime of x is equal to 3x squared minus 6. All right, and so we want to know when this is equal to minus 3. Let's make sure that, yeah, it sounds good. All right, so I want to know when 3x squared minus 6 equals minus 3. Add 3 to both sides. Or, no, even easier. Even easier. Add 6 to both sides. So we're going to add 6 to both sides. And we get 3x squared is equal to 3. Right? What's the answer? Wait, I remember the answer being something different. I'm scared now. Oh, I'm right. Okay. Whew. Whew. See, trying to remember the answer doesn't work. I can't do it, right? You should just trust yourself that you're doing it right. And if you're wrong, well, whatever, right? That's the attitude you should have. All right, so I divide both sides by 3. I get x squared equals 1. So x is equal to plus or minus 1. Now, here's always this sort of, hopefully we're clear about this. Do we want the x values or do we want the coordinates? Here, we wanted the coordinates. So if x equals 1, f of 1 is equal to what? Let's see. 1 cubed is 1, minus 6 times 1 is minus 5. And if x is equal to minus 1, f of minus 1 is equal to 1 cubed is 1 plus 6 times 1 minus 1, right? Is it also minus 5? 5. Plug in minus 1 here to this one. So it's negative 1 plus 5. Yeah, negative 1 plus 6. There we go. Negative 1 plus 6 is 5. Yeah. Whew. Math is hard. All right, so now, did I answer your question? Outstanding. Does anybody have another question they'd like to ask before I just keep on going? By the way, if you ever have a question and I don't see you, what do? Just shout it out. I don't care. You know, that's fine. Hey, I've got a question. I don't understand what you're talking about, Bart. I'm 4 steps behind. Slow down. That's fine. Okay, so last time we talked about the chain rule. The chain rule, if I have a favorite derivative rule, it is the chain rule. I love the chain rule. I can't marry the chain rule, but that's okay. So, oh, come on. Here is a good chain rule question for you. what's the derivative with respect to x of the absolute value of x? How would you do this problem? I mean, absolute value of x, that's like a super easy function, right? If you see a minus sign, you just take it away, right? How would you do this? If we say take the derivative with respect to x of the absolute value of x. It's on the exam, it's on the next exam. You're taking it, what are you going to do? There's two ways to do it. There's like the tough way, and then there's the clever way. The tough way, you say, oh geez, how do I do this? I don't know. The tough way, you break it into cases. You say if x is positive, if x is greater than 0, then the absolute value of x is equal to x, right? And then the derivative, so of the absolute value of x is equal to 1 if x is greater than 0. And you say if x is less than 0, and then the absolute value of x is equal to minus x, right? If x is less than 0. And so d over dx of the absolute value of x is equal to minus 1. And if x equals to 0, well, no derivative exists. Ex. And if you think about the plot of the absolute value of x, absolute value of x looks like, oh, I don't want to, oh. Looks like this, and so there's no derivative, and the derivative of this function looks like that. But that seems really different than what we've been doing, right? This doesn't seem at all to me like the derivatives we've been taking. I broke it into cases. I did all this different stuff. Does anybody know how to write the absolute value of x in a different form? I think I actually told you, although I'm not sure. It's the square root of x squared. The absolute value of x is equal to the square root of x squared. Because you take your favorite negative number, you square it, you get a positive number. Then when we take the square root, we only hand you back the positive number. So the square root of x squared is equal to the absolute value of x. And this function is ripe for using the chain rule. So the derivative of the absolute value of x is equal to the derivative of the square root of x squared. And now I use the chain rule, and let's see, I get the answer to be, I take the derivative of the outside square root, that's x to the 1/2, right? So the 1/2 comes down out in front. So it's going to be 1/2 times, this derivative times the inside to the minus 1/2, because I subtracted 1 for the exponent, times the derivative of the inside. This is the chain rule, right? We did this last time. Times 2x. Done. But wait, remember my answer here? It was like, the derivative is 1 if x is greater than 0. It's 0 if it doesn't exist if x is equal to 0. And over here it's -1. This is like really wordy and stuff. And this is just like some formula. What's going on with this formula? Does anybody know? Let's simplify it. Here, we can simplify things. Sometimes if you simplify things, it makes things easier sometimes. So the 1/2 and the 2 cancel, right? What is to the minus 1/2 power? What does that mean to raise something to the minus 1/2 power? Yeah, it's 1 over the square root. So this is equal to 1 over the square root of x squared times x, right? What's the square root of x squared? What's another way of writing that? Careful. Absolute value of x. You want to say it's x. It's not. Because when I square, if I plug in -3 here, I square it and I get 9. And then I take the square root of 9 and I get 3. I plugged in -3, but I got out 9. I mean 3. So this is equal to x over the absolute value of x. What's that function look like? Plug in 3. What's 3 over the absolute value of 3? 1. Plug in 4. What's 4 over the absolute value of 4? 1, right? Plug in 0. What do you get? It's undefined, just like this function. Plug in -4. What do you get? It'd be -4 divided by 4, so you get -1. So this little function here does everything that our kind of verbose explanation does. Yeah?
You want us to simplify it, or just leave it as...
You don't have to simplify. I'm just showing you what you're getting here. And I don't know about you, but if I can remember back to the time I took Calculus 1, I think this would have freaked me out a little bit if I saw this. And really, you can just plow through it and use the chain rule. Also, this has to do with inverse functions. So be careful. Be very, very careful. Square root of x squared is equal to what? Absolute value of x. How about the square root of x squared? What's that equal to? That's equal to x. What about this one? Sorry, I'm going a little crazy here. The cube root of x cubed. What's that equal to? That's equal to x. And the cube root, oops, other way around. The cube root of x cubed. That's equal to x. What's the deal here? Why do we have this kind of weird asymmetry? What's the deal? What's different about x cubed? Yeah. X cubed can be, the cube root of x can be negative, right? And x cubed is 1 to 1, right? X cubed looks like this. X squared looks like this, not 1 to 1. You guys remember? This is going to come up again pretty soon. So I'm bringing these ideas back. And also, this is a neat application of the chain rule. Also, I don't want this sort of thing to screw you up on an exam, right? If you see absolute value of x, if you're uncomfortable with it, you just replace it with the square root of x squared and go on your merry way. Make sense? All right. What? I said, no, okay. He asked me, is this going to be on the exam? I don't write the exam. They like mail it to me at some point, and I say, oh, okay. I have no idea what's going to be. But I'm just saying, if it's on the exam, I'd hate for you guys to miss this.
Should we use that rule, or should we go with this?
Either one's fine. He says, should I use this one or should I use this one? Either one's fine. If I were you, I'd be a heck of a lot more comfortable with this. Just convert it to this and plow through it with your derivative rules. All right. Any other questions? Yes?
You have one that's like an actual value of x plus 6. You would just do the same thing.
Yeah, absolutely. He said this. He said, what if the problem was, here, let's even make it even worse. Sine of the absolute value of x. No problem. You say this is equal to the derivative of sine of the square root of x squared. I think you use the chain rule. It's perfectly good. It's equal. It really is. All right. Good? So, you might remember, I remember this from high school. I remember this from middle school too. The first things you learn how to plot are lines. Remember plotting lines? Now what's the best formula for a line that you know of? Y equals mx plus b. That's a great line. Y equals mx plus b. M's the slope for some magical reason, and b is the y-intercept for reasons I have no idea. The intercept? I don't know. Anyhow, y equals mx plus b. Is there any problem, by the way, is there any weakness to the y equals mx plus b formula for a line? Any weakness you can think of? There is a, wait, what? Yeah, there is a y-intercept. It's right here. Oh, there isn't a y-intercept, and then it's a vertical line, right? You can't. A vertical line is still a line. Its slope is undefined and has no y-intercept, so this cannot produce. It cannot make vertical lines. And so you probably learned about something called like the standard form for the line. And it looks something like this. AX plus BY equals C. Do you guys remember this for a line, standard form? The only issue here is that, I don't know, if I hand you this line, 3x plus 2y equals 7, can you plot it for me? I mean, can your graphing calculator plot it? No, your graphing calculator cannot plot it. And that's how we like to plot things. We like to plot things with our graphing calculator. It can't do this. Why not?
Two variables.
Two variables? You got to solve for it in terms of y, which you can do here. Not a big deal, but still you're like, damn it, why couldn't you just give it to me in the form y equals mx plus b? Why is this even called the standard form when this one's the more useful way, right? This difference that we're seeing is the difference between an explicit function and an implicit function. Implicit function. And probably you guys have experience with another implicit function. So if you're a curious young 9th grader in high school, you might wonder, you say, well, we can plot lines. I wonder how we plot circles. Maybe. Now, is it easy to plot circles in your graphing calculator? Not so much, right? Because the formula for a circle, well, here's a formula for a circle. X squared plus y squared is equal to 9. This is a circle of radius 3 centered at the origin. And when you try to plot this, you have to plot it in two pieces, because if you try to solve for y, you're going to get plus a square root and minus a square root, right? That's bad. This thing does not plot a function of x. This is also implicit. So we still might want to be able to take its derivative. How do we do this? Let's look at a picture of a circle of radius 3. Here we are. There's 3, there's 3. Circles are going to be green. All right. Draw a nice circle for everybody. It's a little square. There we go. There's my circle. All right, so what's the slope of the tangent line at this point here is 3, 0. What's the slope of the tangent line? It's undefined. Here's the tangent line right there. There's undefined slope. What's the slope of the tangent line at 0, 3? 0. And then we have some other slopes someplace, right? We'd like a formula for the slope of the tangent line. But we don't really want to solve and do algebra with this. We want to be able to sort of take the derivative without solving for y. Let's write that down. That's really important. We want to be able to take the derivative. Can we take the derivative without solving for y? Yes, obviously, otherwise we wouldn't be having this conversation. Right? So yes, yes you can. And let me show you how to do it. Now I remember when I first learned this was pretty confusing to me, so just pay attention and let's see. The first thing you do is you imagine, you use your imagination, you imagine that y is a function of x. Imagine that y is a function of x. And when you want to take the derivative of y, it's easy to do. Here's what it is. Ready? The derivative of y is equal to y prime. I didn't do anything. What's the derivative of y? Y prime. It's a function of x. Right? Okay. Still pretty easy. Let's differentiate our example over here. What you do is you take the derivative of both sides. All right, so d over dx of x squared plus y squared equals d over dx of 9. Now, what's the derivative of, let's do the easy stuff first. What's the derivative of 9? 0. So this whole thing's going to equal 0, whatever it is. What's the derivative of x squared with respect to x? So this is going to be 2x. What's the derivative of y squared? 2y times y prime by the chain rule. You take the derivative of the outside, it's like x squared, right? So the answer is going to be plus 2y times y prime. It's the chain rule.
Why do you use the chain rule on y?
What if I did this? That's a good question. She says, why do you use the chain rule on y? I just erased my beautiful picture. All right. Here it is. What if I wrote it like this? So I have, what if I wrote 2 times y of x squared, like so? So y is something you plug x's into. And so when I take the derivative, not 2, sorry, not 2. I mean, it doesn't matter, but when I take the derivative, I'm going to drop down the 2, take the derivative of the outside. So it's going to be 2 times y of x, 2 times y of x, and now I multiply it by the inside. This is the chain rule, right? Am I answering your question at all?
Yeah.
Okay. So then that's y prime of x. We're saying that you can take its derivative, and whatever it is, it's y prime. What do we do now? We solve for y prime. This will always be easy. If it's not easy, you did something wrong. So how do I solve for y prime? Well, I get 2y equals minus 2x. Oh, where's a y prime here too? Y prime 2y, divide both sides by 2y. Y prime equals minus 2x over 2y equals minus x over y. Let's see if this makes sense. I should have been working on a unit circle. All right, so this point here is 3, 0. What do you get when you plug in 3, 0 to this formula right here? Undefined, right? If I plug in, this point here is 0, 3. What do I get when I plug in 0, 3 to that formula right there? 0. Okay, this point right here, I believe, is 3 over the square root of 2, comma 3 over the square root of 2. Isn't that right? 45 degrees. What do I get here when I plug it in? Don't let the square root of 2's fool you. They all cancel. I get -1. Is -1 a reasonable slope for that tangent line? Absolutely, right? -1 looks like this. What questions do you have about this example? Yeah?
So why don't you take the chain rule of the x plus the y?
Yeah, she says, why don't I take the chain rule for x and just the y? I could, but what's the derivative of x with respect to x? 1. Just kind of stops there. Don't keep on going, because well, now the derivative of 1 is, no, you can't do that, okay? All right, what else? Let's do another example. This example's famous because back in the day, do you guys know who's responsible for us plotting things like this and this? Descartes, the guy who said, I think, therefore I am, wrote all kinds of stuff down, right? Descartes. Descartes had trouble. Descartes was before Newton and Leibniz. He was before calculus, but he could still solve a lot of calculus problems. And he studied this curve, x cubed plus y cubed equals 9xy. This is called the folium of Descartes, and it looks like this. It's kind of a pretty curve. Here we go. Looks kind of like that. It's a little straight. It's more curvy than what I drew, but that's okay. Now see, look, if you tried to solve for y here, I'm guessing we'd have a hard time. Because it's a cubic, for one thing. Quadratics, you should be able to solve any quadratic I throw at you, right? Quadratic formula. Cubic, do any of you know the cubic formula? No, it's harder. It's much harder. And if I just change this to like a 7th degree here, I don't stand a chance. Actually, I don't stand a chance of probably if it's a 4th degree. I'm probably stuck there. Cubic I might be able to do. And 5th degree, it just gets impossible to solve for y after a while. But implicit differentiation, because we're using the chain rule, it will always kick out an extra y prime, and you will always be linear in y prime, so you can always solve, no matter what. So let's go ahead and take the derivative. Let's find dy dx here. So let's see. I write down, I want to compute dy over dx. That's what we want to compute. That's the same thing as the derivative of y with respect to x, right? I know we have different symbols for everything. It's confusing, but that's okay. So we write d over dx of x cubed plus y cubed is equal to d over dx of 9xy. right, what's the derivative of x cubed? 3x squared plus the derivative of y cubed. 3y squared times y prime. You could also write dy dx if you want to. We do that sometimes. All right, it's the same thing. Equals, well, it's going to be 9. What's the derivative of xy? What rule do we have to use? Product rule. Okay, so the derivative of x is it's 1. So it's 9y plus 9 times x times y prime. What do we do now? We just solve for y prime. Is it going to be pretty easy to solve for? It might look bad, but look, it's not as bad. Solving for y here is very hard. Solving for y here, I'm going to do it in less than 1 minute, right? It's not bad at all. Let's see. You get all the y primes on the same side. You get all the other things on the same side. Let's do that. So we have 3y squared times y prime minus 9x times y prime. I'll cross things out as I use them. Boom and boom. Equals 9y minus 3x squared. Look good? Now I factor out the y prime. Y prime, 3y squared minus 9x equals 9y minus 3x squared. And now I can finally solve for y prime. Y prime is equal to 9y minus 3x squared all over 3y squared minus 9x. What do you guys think? Is that right? I don't know. Here, this is going to help us out. Let's see if this works. I know a point on this curve. Yeah, as you can probably guess, can anybody tell me, well, you guys all can. Can anybody tell me a point on this curve? The answer is yes, you all can. 0, 0 is a point on this curve. And what happens when you plug in 0, 0 to that formula there? It's undefined, right? And why should it be undefined? The tangent line has no clue where to go right here. The curve is crossing itself. All right, so that makes sense. Now we need another, if we really want to investigate this, we should have another point. And so the other point on this curve will be 4, it's 4, 2. 4, 2. And what do you think, is the slope positive or negative, or 0, at 4, 2? Positive. It's positive. And maybe, depending on how you look at it, maybe it's, 1 or greater, depending on how good my picture is. I mean, my picture might be pretty crummy, so we'll find out. So let's plug in 4, 2. So the slope at 4, 2 is, let's see, that's 9 times 2 is 18 minus 3 times 4 squared. 4 squared, 16. What's 3 times 16? Minus 48, is that right? 48, okay, great. Divided by 3 times, oh my God, 12. Whew, that wasn't so hard. Minus 12 minus 9 times 4, 36. Okay, 18 minus 48 is it 30? Is that right? Yep. negative 30. And 12 minus 36 is minus 24. Yep. That's 30 over 24. 30 divided by 2 is 15. 24 divided by 2 is 12. 15 over 12. You don't need to simplify, but I'm doing it so I can figure out what the heck's going on. What's the slope of 15 over 12? It's slightly bigger than 1, right? Wait, did I do something wrong? 5 over 4. Yep, you can divide 15 by 3. And 12 by 3. 5 over 4. That's right, 5 over 4. So yeah, that looks about right for right here. That could have a slope of 5 over 4. Does that make any sense? What do you guys think about implicit differentiation? I would expect to see it on your exam. I would expect to see it on a quiz. I don't know, I haven't been paying attention. But what questions do you guys have about this? No, you were first and then I'll call on him.
How did you get 9y plus 9x1?
How did I get 9y right here? This is the product rule. So what you do is you take the derivative of this piece. So the derivative of 9x is 9. There's that 9. And then you multiply it by y. I'm just going to finish it. I think you get it, but I'll finish it. And then you add it to 9x times the derivative of y, which is just y prime. What's your question?
It's always going to be given to us as the equation of a line.
Well, this isn't the equation of a line. Well, this isn't the equation of a line or a circle. So no. But it will be given to you as an equation somehow with x's and y's mixed together. If you see x's and y's mixed together, that's when you use implicit differentiation. All right, let's do some more examples, and then maybe I will push us on to the next chapter just because that's harder stuff. All right, let's do this one. Let's do I'm going to do some different things here. So, compute dy over dx. Does anybody here have trouble remembering if it's dy over dx or dx over dy? Oh, good. Some people. I used to have trouble with this. Okay, so let me see if I can explain where this comes from. So this is like. It's like slope. It's rise over run. We're doing the change in y, that's the rise, over the run. And the run is the x stuff. So it's dy over dx. Does that help anybody? Okay, well, that's good enough for now. Some people said, I don't know. Okay, so it's like the rise over the run. All right, so let's do this one. Let's do the square root of x plus the square root of y equals 9. We got x's and y's mixed together. It would be hard to solve for y. Well, maybe not that hard. I could make it hard to solve for y. Let's not do that though. Okay, so now take the derivative of this. D over dx of the left-hand side, square root of x plus the square root of y equals d over dx of 9. Okay, great. Yeah. All right, so it equals 0. And the derivative of x, the square root of x, is going to be 1/2 x to the minus 1/2. Or 1 over, 2 square root of x. But I'm just a simple person. And then the derivative of this is going to be 1/2 y to the minus 1/2 times y prime, just like in the chain rule, times y prime. Exactly like in the chain rule. Yeah, we're going to keep on going here in just a second. Now I just solve for y prime. So this is 1/2 y to the minus 1/2 times y prime is equal to minus 1/2 x to the minus 1/2. Looking great. Then I divide both sides by this. I get y prime is equal to minus 1/2 x to the minus 1/2 all over 1/2 y to the minus 1/2. Can we simplify this? Yeah, sure, let's do it. The 1/2s cancel to begin with. And this is x to the minus 1/2, so what's going to happen? Everything's going to flip over, so y prime is equal to the square root of y minus the square root of y over the square root of x. It looks similar to the circle, doesn't it? Except you got those square roots in there. Looks very similar to the circle. Is it okay? Can you ask me a question? Why did I flip it? Let me explain that one more time because that's pretty confusing. Remember that x to the minus 1/2, x to the minus 2 is equal to 1 over x squared. 1 over x squared. So 1 over x to the minus 2 is going to be x squared. Is that okay? All right. Yeah.
So the derivative of, like, let's suppose this is the y, the square root of y is 2y. So the derivative is 2y.
You have to find, he says, what's the derivative going to be at, oh wait, 2y prime?
No.
Here?
No, here. The question is square root of x plus 2y.
Oh, he says, what's it going to be if it's 2y? He says, let's change the question. He says, with all these complicated ones, I can see what to do, but actually the simple ones seem a little harder. So he says, what if it's something simple, like you have 2x plus 3y equals 4, right? And I take the derivative of this. I take the derivative of both sides, take derivative of both sides, and we're going to get 2 plus 3y prime equals 0. And look, check this out. Check this out. Here we go. So we have this. So now 3y prime is equal to minus 2. Y prime is equal to minus 2 over 3. This was a line, wasn't it? So the derivative computes the slope of the tangent line, right? What's the slope of this line? Negative 2 over 3, right? If you compute the slope of this line, if you just solve for y, this is 3y equals minus 2x plus 4. Y equals minus 2 over 3x plus 4 over 3. Gave you the right answer. Is it okay? If you're staring at this, you're like, what is that? Is it okay?
Yeah,
Answered your question too. Yeah.
So why does it then compute dy over dx and then solve it in
She says, why do we say, if we say compute dy over dx, why are we doing this? Well, this is when the I'll answer your question. I'm just have to erase some stuff. This is like a character. D over dx walks around and bumps into things. And when he bumps into things, he takes their derivative. And so when he bumps into y here, what happens is the y gets shoved up here, and so it becomes dy over dx. It's the derivative. This is what you get at the end of the day. Did I answer your question, sort of? Yeah. Okay, great. That's amazing. Okay. All right. Let's do a slightly harder problem. dy over dx is equal to y prime. And if you're a physics guru or something like this, sometimes you make a little dot over y, sometimes. All right, so let me double check how much time we have left. I just want to check my phone, check my Facebooks. Let's see. Geez, really. So here's the question I have for you. This is implicit differentiation. It's not so bad. It's a little weird, but not too bad. We're going to use this on Friday and maybe a little bit today, we're not done yet, to compute the derivative of natural log. What could this equal? Can anybody here give me a formula with x's and y's involving natural log? He says e to the y equals x. E to the y equals x. This is true when natural log of x equals y. Is that right? Look at this. We can use implicit differentiation to compute y prime here. Think about that. This is foreshadowing for Friday. All right, we're done. Have a nice day.